Tonight, we're going to explore something that sounds like just another scientific measurement, but is actually the distance that breaks physics itself, the Planck length. You've probably heard this term before. Scientists mention it when talking about quantum mechanics or the smallest scales of reality. It's just 1.6 times 10 to the negative 35th meters, a number so small it seems almost meaningless. But here's what most people don't realize. The Planck length isn't just incredibly tiny, it's the point where everything we know about space and time completely falls apart. Below this distance, the smooth fabric of space-time that Einstein described becomes something else entirely, something we can barely comprehend. It's as if reality itself is pixelated, made of tiny building blocks that our physics cannot describe. This isn't just an academic curiosity. The Planck length represents the absolute limit of physical measurement, the boundary where our most fundamental theories break down and new unknown laws of nature must take over. By the end of tonight, you're going to understand why this impossibly small distance holds the key to the biggest unsolved mysteries in physics and why it might completely change how we see reality itself. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small gesture for you, but it makes a huge difference for me. Now let's begin. You live in a universe of boundaries. Every day, without thinking about it, you encounter limits that define the very fabric of reality. There's a maximum speed at which information can travel through space, a boundary set by light itself at roughly 300 million meters per second. There's a minimum temperature, absolute zero, where all atomic motion ceases at negative 273 degrees Celsius. And there's a fundamental constant that governs how energy is packaged in the quantum world, Planck's constant, determining the smallest possible action in nature. These aren't arbitrary human constructs or mathematical conveniences. They're written into the architecture of existence itself, unchangeable rules that have governed every moment since the universe began. But perhaps the most profound boundary of all is one you've likely never considered, even though it shapes everything you see, touch, and experience. It's a limit on smallness itself, a distance so tiny that it defies comprehension, yet so fundamental that it may hold the key to understanding why anything exists at all. This boundary is called the Planck length, and it represents something extraordinary in the realm of physics, the point where space itself breaks down. To understand what this means, you need to step back and consider what we mean when we talk about the limits of the universe. When astronomers speak of boundaries, they often refer to the edge of the observable cosmos, that sphere of view, space roughly 93 billion light-years across, that represents how far light has travelled since the Big Bang. But this is just a boundary of observation, not of reality itself. The actual universe may be infinite, stretching endlessly in all directions, filled with galaxies and structures we'll never see because their light hasn't had time to reach us. The Planck length is different. It's not about how far we can see or how much we can discover. It's about the fundamental structure of space and time themselves. At 1.6 times 10 to the negative 35th meters, this distance is so small that comparing it to anything in your everyday experience becomes meaningless. An atom is to the Planck length as the entire observable universe is to the period at the end of this sentence. It's a scale where our normal concepts of measurement, distance, and even existence lose their meaning. Yet this impossibly tiny distance may be the most important measurement in all of physics. Just as the speed of light sets an absolute limit on how fast anything can travel through the universe, the Planck length appears to set an absolute limit on how small any meaningful distance can be. Below this scale, the very concepts of space and time that Einstein wove together in his theory of relativity begin to unravel. The smooth, continuous fabric of space-time that curves around massive objects and carries gravitational waves across the cosmos transforms into something else entirely, something that our current understanding of physics cannot describe. This isn't simply a matter of our instruments being too crude to measure such tiny distances, though they certainly are. Even with perfect measuring devices, physics itself suggests that distances smaller than the Planck length are fundamentally unmeasurable, not because of technological limitations, but because the act of measurement requires energy, and the energy needed to probe such small scales would be so enormous that it would collapse into a black hole, destroying both the measuring device and the thing being measured. The Planck length emerges naturally from the intersection of three fundamental constants of nature: the speed of light, which governs the structure of space-time; Planck's constant, which governs quantum mechanics; and the gravitational constant, which governs how matter and energy warp the fabric of space. When you combine these three pillars of modern physics in just the right way, out comes this tiny distance, as if nature itself is telling us that here, at this scale, something fundamental changes. What makes this boundary so remarkable is that it represents the scale where quantum mechanics and gravity, the two great theories of 20th century physics, must finally confront each other. Throughout most of the universe, these two frameworks operate in separate domains. Gravity dominates on large scales, governing the motion of planets and the expansion of space, while quantum mechanics rules the microscopic world of atoms and particles. But at the Planck scale, both become equally important, and that's where our current understanding breaks down. The implications are staggering. If space itself has a fundamental granular structure at the Planck scale, then the universe isn't the smooth, continuous realm that our everyday experience suggests. Instead, it might be more like a vast digital image, appearing smooth from a distance, but revealing discrete pixels when you zoom in far enough. This pixelation of reality would mean that space and time don't flow continuously, but come in tiny, indivisible chunks, each no smaller than 1 Planck length across, and lasting no less than 1 Planck time, about 5.4 times 10 to the negative 44 seconds. This boundary forces us to confront profound questions about the nature of reality itself. If there truly is a smallest possible distance, what does that mean for our understanding of infinity? If space is quantized into discrete units, how do objects move smoothly through it? And perhaps most mysteriously of all, what lies beyond this boundary? Is there a deeper layer of reality from which space and time themselves emerge, or does the question itself lose meaning at such scales? The Planck length stands as both a testament to human ingenuity in uncovering the hidden structure of reality and a humbling reminder of how much we still don't know. It marks the frontier where known physics ends and new mysteries begin, a boundary that may hold the secrets to understanding not just how the universe works, but why it exists at all. To truly appreciate the profound nature of the Planck length, you need to understand just how vast the scale of the universe really is, and how the concept of small itself changes as we journey deeper into the heart of reality. The cosmos presents us with scales so extreme that they challenge our ability to comprehend them, stretching from the incomprehensibly large to the infinitesimally tiny, with human experience occupying just a narrow slice somewhere in between. Consider for a moment the observable universe, that sphere of space containing everything we can possibly see. At roughly 93 billion light-years across, it encompasses billions of galaxies, each containing hundreds of billions of stars. To put this in perspective, if you could shrink the Earth down to the size of a marble, the observable universe would still be larger than the Earth's actual orbit around the Sun. This is the scale of the incomprehensibly large, where distances are measured in units so vast that light, travelling at 300 million meters per second, takes billions of years to cross them. Now imagine zooming in, beginning a journey toward the incomprehensibly small. Start with something familiar: yourself. You're roughly 2 meters tall, composed of about 37 trillion cells, each one a complex factory of molecular machinery. but you're still operating at what physicists call the macroscopic scale, where the familiar laws of classical physics govern everything from the motion of your limbs to the beating of your heart. Zoom in by a factor of 1,000 and you enter the microscopic world. Here, a single millimeter becomes a vast landscape. The cells that make up your body, typically about 10 to 20 micrometers across, are revealed as intricate structures with boundaries, internal compartments, and molecular machinery more complex than any factory ever built by human hands. The proteins folding inside these cells, the DNA storing genetic information, the mitochondria producing energy, all operate at scales where a micrometer, 1/1,000,000th of a meter, becomes a meaningful unit of measurement. Continue your journey inward by another factor of 1,000, and you reach the nanoscale, where individual molecules become visible. Here, a nanometer, 1/1000,000th of a meter, is the natural unit of measurement. This is the scale of DNA's double helix, about 2 nanometers wide, and of the complex proteins that carry out the chemistry of life. It's also the scale where human technology has learned to manipulate individual atoms, building structures one atomic layer at a time. Push deeper still, and you encounter the atom itself, roughly 1/10th of a nanometer across. For most of human history, atoms were considered the fundamental building blocks of matter, indivisible units from which everything else was constructed. The word atom itself comes from the Greek atomos, meaning uncuttable. Yet your journey toward the small has barely begun. The atom, vast as it seemed to early scientists, is mostly empty space. If an atom were scaled up to the size of a football stadium, its nucleus would be smaller than a marble sitting at the center of the field. Zoom in by another factor of 10,000 and you reach the nucleus, where protons and neutrons cluster together in a space just a few femtometers across. A femtometer is 1/4,000,000th of a meter, so small that light, which seems instantaneous in your everyday experience, takes several times longer to cross a proton than it takes to cross the distance from the Earth to the Moon. Here, in the realm of nuclear physics, the strong force dominates, binding protons and neutrons together with an intensity that dwarfs the electromagnetic forces that hold atoms together. But even protons and neutrons aren't fundamental. Push deeper, and you discover that they're made of even smaller constituents called quarks, bound together by the exchange of particles called gluons. Quarks exist at scales of about 1 atometer, 1/quintillionth of a meter. This is approaching the limits of what we can currently explore with our most powerful particle accelerators, machines that slam particles together at nearly the speed of light to probe the structure of matter at its deepest levels. Yet we're still 20 orders of magnitude away from the Planck length. 20 factors of 10 separate the smallest scales we can currently probe from that ultimate boundary where physics itself breaks down. To put this in perspective, the difference between a quark and the Planck length is greater than the difference between a human being and the entire observable universe. This is where the concept of small begins to lose its familiar meaning. In your everyday experience, small things are simply miniature versions of larger things. A toy car is small compared to a real car, but it has the same basic features: wheels, doors, seats. As you journey deeper into the microscopic realm, this relationship initially holds. Cells are like tiny cities, molecules like tiny machines, atoms like tiny solar systems with electrons orbiting a central nucleus. But as you approach truly fundamental scales, this analogy breaks down completely. The quantum world operates according to principles that have no counterpart in your everyday experience. Particles exist in multiple states simultaneously, pop in and out of existence, and influence each other instantaneously across vast distances. Space and time themselves begin to fluctuate and blur, becoming uncertain and probabilistic rather than fixed and definite. At the Planck length, even these strange quantum principles may no longer apply. This is the scale where space itself might be quantized, broken into discrete units like the pixels of a digital image. Below this scale, the very concepts of distance, duration, and causality that form the foundation of physics may lose their meaning entirely. Here, at the boundary between the known and the unknowable, our journey toward the small reaches its ultimate destination, the point where the familiar universe ends and something entirely new begins. In the early decades of the 20th century, physicists made a discovery that would forever change our understanding of the universe. Nothing can travel faster than light. This revelation didn't come from observing distant stars or cosmic phenomena, but from wrestling with the fundamental nature of space and time themselves. The speed of light, 299,792,458 meters per second, isn't just the speed at which photons happen to move through empty space. It's the cosmic speed limit, the maximum rate at which any information, energy, or influence can propagate through the universe. This speed limit is built into the very fabric of space-time. When Albert Einstein formulated his theory of special relativity, he showed that space and time are not separate, independent entities, but are woven together into a four-dimensional continuum. In this unified space-time, the speed of light represents something profound. It's the rate at which cause and effect can propagate, the maximum speed at which the future can influence the past, the ultimate boundary that separates what can be connected from what must remain, forever isolated. What makes this speed limit so remarkable is its absolute nature. Unlike speed limits on highways, which depend on local conditions and can be changed by human decree, the speed of light is written into the mathematical structure of reality itself. It emerges naturally from the geometry of space-time, from the way that space and time are related to each other. No amount of energy, no matter how cleverly applied, can accelerate any object with mass to reach or exceed this cosmic boundary. The implications of this limit ripple through every aspect of physics and cosmology. It means that the universe has a finite age. If light has been traveling for 13.8 billion years since the Big Bang, then we can see objects only within that distance. It means that simultaneity is relative. Events that appear to happen at the same time to one observer may occur at different times to another observer moving at high speed. It means that space and time themselves are elastic, stretching and compressing as objects accelerate through the cosmos. But perhaps most importantly, the speed of light as an absolute limit introduces us to a crucial concept: the idea that the universe has fundamental boundaries written into its very structure. These aren't practical limitations imposed by our technology or understanding, but absolute constraints that no physical process can violate. The speed of light is one such boundary, governing motion through space. Temperature has another such boundary at absolute zero, where all thermal motion ceases. And as we've begun to explore, there appears to be a boundary governing space itself. Just as nothing can move faster than light through space, there may be a limit to how finely space can be divided. The Planck length represents this potential boundary, not a speed limit, but a space limit. Just as the speed of light emerges from the fundamental constants that govern electromagnetic phenomena, the Planck length emerges from the fundamental constants that govern space, time, and gravity. The parallel between these two limits is more than metaphorical. Both arise from the same deep principle, that the universe operates according to precise mathematical laws with built-in constraints. The speed of light limit prevents paradoxes in causality. If information could travel faster than light, effects could precede their causes, leading to logical contradictions that would undermine the rational structure of physics. Similarly, the Planck length limit may prevent paradoxes in the structure of space itself. Consider what happens when you try to probe distances smaller than the Planck length. According to quantum mechanics, examining something at a particular scale requires photons with enough energy to resolve that scale. The shorter the distance you want to measure, the more energetic the photons must be. But as you increase the energy of your measuring photons to probe smaller and smaller scales, something remarkable happens. The energy becomes so concentrated that it curves spacetime around itself, eventually forming a black hole that destroys both your measuring device and whatever you were trying to measure. This isn't a failure of technology or technique, it's a fundamental limit imposed by the laws of physics themselves. The Planck length represents the point where the energy required for measurement becomes so large that it fundamentally alters the space being measured. Beyond this boundary, the very act of observation changes the nature of reality so completely that the concept of measurement loses its meaning. This creates a profound parallel with the speed of light. Just as attempting to accelerate past the speed of light would require infinite energy and is therefore impossible, attempting to measure distances smaller than the Planck length would require so much energy that it destroys the measurement itself. Both limits protect the logical consistency of physics, preventing scenarios that would lead to contradictions and paradoxes. The existence of these absolute boundaries suggests something remarkable about the nature of reality. The universe appears to be constructed with built-in safeguards that preserve its own logical coherence. The speed of light prevents causal paradoxes. Absolute zero prevents temperatures from becoming meaninglessly low. The uncertainty principle prevents us from knowing both the position and momentum of a particle with perfect precision. And the Planck length may prevent space itself from being divided into meaninglessly small pieces. These boundaries aren't obstacles to understanding, they're clues to the deeper structure of reality. They tell us that the universe isn't an arbitrary collection of phenomena, but a carefully balanced system governed by precise mathematical relationships. Each limit reveals something fundamental about how reality is constructed, about the rules that govern existence at its most basic level. The speed of light taught us that space and time are unified and relative. The Planck length may be preparing to teach us something equally profound about the nature of space itself, that it too has a fundamental structure, a smallest meaningful scale beyond which our current concepts of distance and measurement simply don't apply. In recognizing these limits, we begin to glimpse the true architecture of existence, built not from arbitrary rules, but from mathematical necessities that ensure the universe remains logically consistent and comprehensible. In the early 1900s, as physicists peered deeper into the heart of matter, they discovered something that challenged every intuition about how the world works. The realm of atoms and particles didn't behave like a scaled-down version of the familiar macroscopic world. Instead, it operated according to principles so strange and counterintuitive that even the scientists who discovered them struggled to accept what they were seeing. This was the birth of quantum mechanics, a theory that would revolutionize our understanding of reality and ultimately lead us to contemplate the very limits of space itself. The quantum world revealed that at the smallest scales, reality becomes fundamentally probabilistic rather than deterministic. Unlike the clockwork universe of classical physics, where every effect has a precise cause and the future can be calculated from the present with mathematical certainty, quantum mechanics showed that particles exist in states of pure possibility until the moment they're observed. An electron doesn't orbit an atom like a miniature planet following a predictable path. Instead, it exists as a cloud of probability, simultaneously occupying all possible positions until something forces it to choose a specific location. This wasn't simply a matter of incomplete knowledge or imprecise measurements. The probabilistic nature of quantum mechanics is built into the fabric of reality itself. When you fire a single photon at a barrier with two slits, quantum mechanics tells us that the photon, somehow passes through both slits simultaneously, interfering with itself to create a pattern that's impossible to explain if the photon had taken only one definite path. Yet the moment you try to observe which slit the photon actually passes through, the quantum superposition collapses, and the photon behaves like a classical particle, choosing one slit or the other. This bizarre behavior becomes even more mysterious when you consider the process of quantum measurement. In the classical world, measurement is a passive act of observation that reveals pre-existing properties. When you measure the length of a table, you're discovering something that was already true about the table before you measured it. But in the quantum world, measurement is an active process that creates the very properties it appears to be discovering. Before measurement, a quantum particle doesn't have a definite position or momentum or spin. These properties come into existence only through the act of observation. The implications extend far beyond individual particles. Quantum mechanics revealed that the vacuum of space itself isn't empty, but seethes with activity. Even in the apparent emptiness between stars and galaxies, quantum fields fluctuate constantly, creating virtual particles that pop in and out of existence in timeframes so brief they seem to violate the conservation of energy. These quantum fluctuations aren't just theoretical curiosities, they have measurable effects on the behavior of atoms and the structure of space-time itself. As physicists developed increasingly sophisticated ways to probe smaller and smaller scales, the quantum strangeness only intensified. At the scale of atomic nuclei, particles began to exhibit behaviors that had no analogue in the classical world. Protons and neutrons weren't solid objects, but complex dynamic structures composed of quarks bound together by forces that operated according to rules unlike anything in everyday experience. The strong nuclear force that binds quarks together actually grows stronger as you try to pull them apart, making it impossible to isolate individual quarks, no matter how much energy you apply. This journey into the quantum realm forces us to confront a profound question. If reality becomes increasingly strange and counterintuitive as we examine smaller scales, what happens when we push our inquiry to its absolute limit? What does quantum mechanics predict about the nature of space and time themselves at the smallest possible scales? The answer leads us directly to one of the most unsettling implications of quantum mechanics: the idea that there may be a fundamental limit to how precisely we can examine the structure of space. Just as Heisenberg's uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision, there may be an uncertainty principle governing space and time themselves. Consider what happens as you attempt to zoom into ever smaller regions of space. Classical physics suggests that this process could continue indefinitely, revealing finer and finer details without limit. Space, in this view, is infinitely divisible, smooth and continuous at all scales, like a perfect mathematical line that contains an infinite number of points no matter how small a segment you examine. But quantum mechanics suggests otherwise. The very act of probing small distances requires energy, and as you attempt to examine smaller and smaller regions, the energy requirements grow enormous. At some point, the energy needed to probe a particular scale becomes so large that it begins to significantly affect the space being examined, creating quantum fluctuations that obscure the very measurement you're trying to make. This isn't just a practical limitation of our measuring instruments, it's a fundamental constraint imposed by the laws of physics themselves. The uncertainty inherent in quantum mechanics means that space itself becomes uncertain at sufficiently small scales. The smooth, continuous fabric of space-time that Einstein described in his theory of general relativity gives way to a realm where the very concepts of distance and duration become fuzzy and probabilistic. In this quantum foam, as physicists call it, the familiar geometry of space breaks down completely. Distances become uncertain, Durations become indefinite, and the clear distinction between past and future begins to blur. The rigid stage upon which classical physics plays out transforms into something more like a turbulent ocean, where waves of probability crash and interfere with each other in patterns too complex and chaotic for classical mathematics to describe. This quantum uncertainty in the structure of space itself points toward a fundamental limit, a scale beyond which our usual concepts of measurement and distance lose their meaning. That scale is the Planck length, where quantum mechanics and gravity converge to create a boundary beyond which physics as we know it simply cannot penetrate. Here, in this realm of ultimate uncertainty, space itself becomes subject to the probabilistic laws of quantum mechanics, fluctuating and shifting in ways that challenge our deepest assumptions about the nature of reality. The Planck length emerges from the deepest mathematics of physics like a whisper from the fundamental structure of reality itself. At 1.6 times 10 to the negative 35th meters, this distance represents far more than just an extremely small measurement. It marks the boundary where our most successful theories of physics, quantum mechanics, and general relativity converge to reveal something profound and unsettling about the nature of space and time. To understand why this particular distance is so significant, you need to appreciate how it arises naturally from the three most fundamental constants in physics. The first is the speed of light, that cosmic speed limit which governs how fast information can travel through space-time. The second is Planck's constant, the quantum of action that sets the scale for all quantum mechanical phenomena. The third is Newton's gravitational constant, which determines how strongly matter and energy curve the fabric of space-time. When you combine these three constants in precisely the right mathematical way, out comes the Planck length, as if the universe itself is revealing a fundamental scale built into its very architecture. What makes this distance so mysterious is that it represents the scale where quantum mechanics and gravity become equally important. Throughout most of the universe, these two great theories operate in separate domains. Gravity dominates at large scales, governing the motion of planets, the formation of galaxies, and the expansion of the universe itself. Meanwhile, quantum mechanics rules the microscopic realm, determining how atoms bind together, how particles interact, and how energy flows through matter. But at the Planck scale, both theories demand equal attention, creating a situation that our current physics simply cannot handle. This convergence creates what physicists call a fundamental barrier to measurement. The very act of trying to probe distances at or below the Planck length runs into an insurmountable problem rooted in the uncertainty principle that governs all quantum measurements. Werner Heisenberg's uncertainty principle tells us that there are fundamental limits to how precisely we can know certain pairs of properties about quantum systems. The more precisely you determine a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments, it's built into the quantum mechanical description of reality itself. At the Planck scale, this uncertainty principle takes on cosmic significance. To measure distances approaching the Planck length, you would need to use photons with enormous energy, photons whose wavelengths are comparable to the tiny distances you're trying to probe. But here's where the fundamental problem emerges. According to Einstein's theory of general relativity, energy curves space-time, and the more energy you concentrate in a small region, the more dramatically space-time curves. The energy required to probe the Planck scale is so enormous that it would curve space-time so severely that it would form what physicists call a micro-black hole. This micro-black hole would have an event horizon roughly the size of the Planck length itself. Beyond this horizon, no information can escape, making any measurement impossible. The very tool you need to probe the smallest scales of space creates a gravitational barrier that prevents you from seeing what you're trying to measure. It's as if the universe has built-in protection against being examined too closely, a fundamental privacy shield that operates at the deepest level of reality. The implications of this measurement barrier extend far beyond practical concerns about experimental limitations. It suggests that the Planck length represents a fundamental granularity in the structure of space itself. Just as digital images are composed of discrete pixels that create the illusion of smooth curves and gradual changes when viewed from a distance, space might be composed of discrete units at the Planck scale, creating the illusion of smooth continuity that we observe in our everyday experience. This pixelation of space would mean that the universe operates more like a vast three-dimensional grid than the smooth continuum that classical physics describes. Each unit of this grid would be one Planck length across, and nothing smaller than this fundamental pixel could have any meaningful existence. Movements through space wouldn't be perfectly continuous, but would occur in tiny, discrete jumps from one grid point to another, like the movement of a character in an early video game. The concept challenges our deepest intuitions about the nature of infinity and continuity. If space truly has a smallest meaningful unit, then the mathematical concept of infinite divisibility that underlies calculus and much of modern physics might not correspond to physical reality. The smooth functions and continuous curves that physicists use to describe everything from planetary orbits to quantum wave functions might be approximations that work well at large scales, but break down when applied to the fundamental structure of space-time itself. This breakdown of classical concepts at the Planck scale extends to time as well as space. Just as there appears to be a smallest meaningful distance, there also appears to be a smallest meaningful duration, the Planck time, roughly 5.4 times 10 to the negative 44 seconds. This incredibly brief interval represents the time it takes light to travel one Planck length, and it may represent the smallest unit of temporal experience that the universe allows. Together, the Planck length and Planck time suggest that space-time itself might be quantized, broken into discrete, indivisible units like the energy levels of quantum mechanical systems. This quantum geometry would mean that the stage upon which all physical processes play out is not the smooth, continuous arena that Einstein envisioned, but something more like a four-dimensional crystal lattice with specific, unchangeable proportions built into its structure. The mysteries of the Planck scale force us to confront profound questions about the relationship between mathematics and physical reality. The equations that describe quantum mechanics and general relativity break down at this scale, yielding infinite results that have no physical meaning. This mathematical crisis suggests that our current theories are incomplete, that they represent approximations to some deeper truth that governs the universe at its most fundamental level. The Planck length stands as a signpost pointing toward this unknown territory, marking the boundary where known physics ends and profound mystery begins. When Albert Einstein first conceived of space-time as a unified four-dimensional continuum, he revolutionized our understanding of the universe's most fundamental stage. In his vision, space and time weren't separate entities, but were woven together into a seamless fabric that could bend, stretch, and ripple in response to the presence of matter and energy. This space-time wasn't just the empty container in which events occurred, it was a dynamic participant in every physical process, curving around massive objects to create what we experience as gravity, and propagating disturbances as gravitational waves that carry information across the cosmos at the speed of light. This geometric picture of space-time possesses an elegant mathematical beauty that has captivated physicists for more than a century. In Einstein's equations, space-time is described as a smooth manifold, a mathematical structure that looks locally flat and continuous no matter how closely you examine it. Like a perfectly polished marble surface, this space-time fabric appears uniform and seamless at every scale. infinitely divisible into smaller and smaller regions without ever revealing any fundamental granularity or underlying structure. The smoothness of classical spacetime is more than just a mathematical convenience, it's essential to how general relativity works. The theory depends on the idea that you can define precise locations in space and exact moments in time, and that objects can move along perfectly continuous paths through this four-dimensional continuum. Gravitational fields vary smoothly from point to point, creating gradual changes in the curvature of space-time that guide the motion of everything from photons to planets. The equations that govern this behavior rely on calculus, the mathematics of continuous change, which assumes that you can always zoom in to examine space-time at finer and finer scales without limit. This continuity allows general relativity to make remarkably precise predictions about phenomena ranging from the precession of Mercury's orbit to the detection of gravitational waves from colliding black holes billions of light-years away. The theory's success in describing the large-scale structure and evolution of the universe provides powerful evidence that space-time behaves as a smooth continuum at the scales we can directly observe and measure. But as you journey towards smaller scales, this picture of smooth, continuous space-time begins to encounter fundamental challenges. The first hints of trouble appear when you consider the energy requirements for probing increasingly tiny regions of space. To examine the geometry of space-time at a particular scale, you need to send test particles or photons into that region and observe how they behave. The smaller the scale you want to investigate, the higher the energy these probe particles must possess. As the required energies grow larger, something remarkable begins to happen. The probe particles themselves start to influence the space-time they're meant to be measuring. Their energy contributes to the stress-energy tensor that appears on the right side of Einstein's field equations, causing the space-time geometry to curve in response to their presence. At sufficiently small scales and high energies, this effect becomes so pronounced that the act of measurement significantly alters the quantity being measured. This problem becomes catastrophic as you approach the Planck scale. The energy required to probe distances comparable to the Planck length is so enormous that it creates such extreme curvature in space-time that the measurement process destroys itself. The probe particles carry so much energy that they collapse into black holes, creating event horizons that hide the very information you were trying to gather. The smooth fabric of space-time, when examined too closely, reveals its own limits and begins to protect itself from further scrutiny. But the breakdown of smooth space-time at the Planck scale involves more than just measurement problems. Quantum mechanics introduces a fundamental fuzziness into the very concept of geometric precision. The uncertainty principle that governs quantum measurements doesn't just apply to the positions and momenta of particles, it extends to the structure of space-time itself. At sufficiently small scales, the geometry of space and time becomes subject to quantum fluctuations that blur the sharp distinctions between here and there, between now and then. These quantum fluctuations in space-time geometry create what physicists call quantum foam, a seething, chaotic realm where the smooth manifold of classical general relativity gives way to something far more turbulent and unpredictable. In this foam, virtual particles pop in and out of existence on timescales so brief they seem to violate energy conservation, while the geometry of space-time itself fluctuates wildly, creating temporary shortcuts through space, microscopic wormholes, and regions where the usual rules of causality break down. The transition from smooth space-time to quantum foam represents one of the most profound challenges in modern physics. It suggests that the continuous, deterministic picture of space-time that works so well at large scales is fundamentally incomplete. At the deepest level, space and time may not be the smooth, infinitely divisible continuum that classical physics assumes, but rather something more like a turbulent ocean, whose apparent smoothness emerges only when viewed from a sufficiently large distance. This breakdown of continuity has profound implications for our understanding of geometry itself. If space-time is not infinitely smooth, then the mathematical foundations of general relativity, which depend on the ability to define precise points in space and time, may require fundamental revision. The calculus that describes how space-time curves in response to matter and energy assumes that you can always take derivatives and integrals at arbitrary precision. But if space and time come in discrete, indivisible chunks, these mathematical operations may lose their physical meaning at the smallest scales. The emergence of granularity in space-time would represent a return to an ancient philosophical debate about the nature of space and time. Is the universe made of discrete, indivisible atoms of space and time, or is it a smooth continuum that can be divided without limit? The Planck length suggests that this question may have a definitive answer. Space and time themselves may be quantized, possessing a fundamental granular structure that becomes apparent only when we push our investigations to their absolute limits. At this boundary, the smooth geometry that Einstein revealed begins to give way to something entirely new, a quantum geometry that challenges our most basic assumptions about the nature of reality itself. Imagine looking at a photograph from across a room. The image appears smooth and continuous, with gentle gradations of color and tone that create the illusion of a seamless representation of reality. But as you step closer and closer to the photograph, something remarkable begins to happen. The smooth curves and subtle transitions start to reveal their underlying structure. What seemed like continuous color becomes a collection of discrete dots, each one a tiny pixel of specific hue and brightness. Up close, the illusion of smoothness dissolves, revealing the fundamental granular nature of the digital image. This transformation from apparent continuity to revealed discreteness may offer us the most profound insight into the nature of space itself. Just as digital images create the illusion of smoothness through the clever arrangement of discrete pixels, the universe may create the illusion of smooth continuous space through the arrangement of fundamental units at the Planck scale. The fabric of reality, when examined at its deepest level, might not be the seamless continuum that our everyday experience suggests, but rather something more like a vast three-dimensional grid composed of indivisible units of space and time. This concept of pixelated space emerges naturally from the mathematical structure of quantum mechanics and the fundamental limits imposed by the Planck length. If there truly is a smallest meaningful distance in the universe, a length below which the very concept of measurement breaks down, then space itself must be composed of discrete, indivisible units. Each unit would be one Planck length across, creating a cosmic grid so fine that its granular structure remains invisible at every scale we can observe, yet so fundamental that it underlies every physical process in the universe. In this pixelated reality, the smooth motion that characterizes your everyday experience would be revealed as an illusion created by rapid jumping from one discrete location to another. A particle moving through space wouldn't follow a perfectly continuous path, but would hop from grid point to grid point, like a character in an early video game moving across a pixelated landscape. The apparently smooth trajectory would emerge from the averaging of countless tiny discrete jumps, each one spanning exactly one unit of the cosmic grid. This discretization of space would have profound implications for our understanding of geometry and motion. The curves and smooth surfaces that mathematicians have studied for centuries might be approximations that work well at large scales, but break down when applied to the fundamental structure of reality. A circle, in this pixelated universe, wouldn't be a perfect curve, but a polygon with an enormous number of sides, each side exactly one Planck length long. The precise mathematical relationships that govern classical geometry, like the ratio of a circle's circumference to its diameter, might be cosmic approximations that emerge from the underlying discrete structure rather than exact truths about the nature of space. The implications extend beyond geometry to the very nature of physical fields and forces. In classical physics, electromagnetic fields and gravitational fields are described as smooth functions that vary continuously from point to point in space. But if space is fundamentally pixelated, these fields would be more like cellular automata, with each cell of the cosmic grid containing specific values that influence the values in neighboring cells according to precise rules. The smooth field equations that describe electromagnetic and gravitational phenomena would be emergent properties of these underlying discrete interactions. This pixelation would also revolutionize our understanding of symmetries in physics. Many of the most important principles in modern physics depend on the assumption that space is perfectly homogeneous and isotropic, that it looks the same at every point and in every direction. But a pixelated space would necessarily break these symmetries at the Planck scale, introducing a preferred coordinate system defined by the orientation of the cosmic grid. The continuous symmetries that physicists have identified as fundamental to the laws of nature might be approximate symmetries that emerge when you average over many grid cells, rather than exact symmetries built into the structure of spacetime itself. The concept of pixelated space also suggests a natural resolution to some of the infinities that plague quantum field theory. In the current formulation of quantum mechanics, certain calculations yield infinite results that must be artificially removed through mathematical procedures called renormalization. But if space is fundamentally discrete, these infinities might disappear naturally. The grid structure would provide a natural cutoff for quantum fluctuations, preventing them from extending to arbitrarily small scales where they would contribute infinite energy to physical processes. Perhaps most remarkably, this pixelated structure might explain why the universe appears to be expanding. If space is fundamentally discrete, then the expansion of the universe might not be a stretching of smooth space-time, but rather an increase in the number of grid cells between any 2 points. New units of space might be constantly created, inserting themselves into the cosmic grid and pushing existing matter apart. The cosmic expansion wouldn't be objects moving through space, but space itself multiplying, adding new pixels to the cosmic image of reality. The resolution of this cosmic grid would be so fine that it would remain completely invisible at every scale we can observe. The Planck length is so small compared to atoms, molecules, or even subatomic particles that billions upon billions of grid cells would fit within the smallest structures we can detect. The pixelation would be like trying to see the individual pixels in a photograph from many miles away. The discrete structure would be completely hidden by the limitations of our observational capabilities. Yet this hidden pixelation might hold the key to understanding some of the deepest mysteries in physics. The apparent smoothness of space at observable scales might be telling us something profound about how complex, continuous-seeming phenomena can emerge from simple, discrete underlying rules. Just as the rich complexity of life emerges from the simple digital code of DNA, and just as the smooth curves of computer graphics emerge from the manipulation of discrete pixels, the elegant continuity of space-time might emerge from the interactions of fundamental units of pixelated space, each one exactly 1 Planck length across, each one a tiny building block in the vast digital architecture of reality itself. The Planck length stands as perhaps the most unbreakable rule in all of physics, a boundary written into the fundamental architecture of reality that cannot be crossed, circumvented, or violated by any known process. Unlike human-made rules that can be changed by decree or natural laws that might be modified by future discoveries, the Planck length emerges from the deepest mathematical relationships that govern existence itself. It represents not just a practical limitation of our current understanding, but a fundamental constraint that appears to be woven into the very fabric of space-time. What makes this boundary so absolute is its origin in the most basic constants of nature. The Planck length arises from the intersection of quantum mechanics, relativity, and gravity, the three pillars upon which our understanding of the universe rests. When you combine the speed of light, Planck's constant, and Newton's gravitational constant in the precise mathematical relationship that defines the Planck length, you're not performing an arbitrary calculation. You're uncovering a fundamental scale that nature itself has embedded in the structure of reality. This mathematical inevitability suggests that the Planck length isn't merely a human construct or a convenient unit of measurement. It's a distance that emerges naturally from the laws of physics themselves, a scale that would be discovered by any sufficiently advanced civilization anywhere in the universe. The same combination of constants that yields the Planck length on Earth would yield identical results for alien physicists studying the cosmos from distant galaxies. This universality points to something profound. The Planck length represents a fundamental property of the universe itself, not just of our particular corner of it. The unbreakable nature of this rule becomes apparent when you consider what happens if you try to violate it. Any attempt to measure or probe distances smaller than the Planck length runs into an insurmountable barrier rooted in the fundamental laws of physics. The energy required to examine such tiny scales becomes so enormous that it warps spacetime so severely that measurement becomes impossible. The universe seems to protect itself from being examined too closely, as if there's a cosmic privacy screen that prevents us from peering beyond this fundamental boundary. This protection mechanism operates through the interplay of quantum mechanics and general relativity. As you concentrate more and more energy into smaller and smaller regions to probe tinier distances, the gravitational effects of that energy become increasingly important. Eventually, you reach a point where the energy density becomes so extreme that it creates a black hole whose event horizon is comparable to the distance you're trying to measure. At this point, the very tool you're using to examine space creates a gravitational barrier that hides the information you're seeking. The Planck length thus represents what physicists call a natural cutoff, a scale beyond which the usual rules of physics break down and new unknown principles must take over. This isn't simply a matter of our current theories being incomplete, though they certainly are. It's a fundamental statement about the nature of physical reality. There appears to be a smallest meaningful distance in the universe, below which the concepts of space and time themselves lose their familiar meaning. This breakdown of familiar concepts has profound implications for our understanding of the structure of reality. If the Planck length truly represents a fundamental limit, then the universe operates more like a digital system than the analog continuum that classical physics describes. Space might be quantized into discrete units, each exactly one Planck length across, creating a cosmic grid that underlies all physical processes. Time might similarly be quantized into discrete moments, each lasting exactly one Planck time, the brief interval it takes light to travel one Planck length. The implications of this quantization extend throughout physics. Many of the mathematical tools that physicists use to describe natural phenomena depend on the assumption that space and time are infinitely divisible. Calculus, the mathematics of continuous change that underlies most of modern physics, assumes that you can always examine smaller and smaller intervals without limit. But if space and time come in discrete, indivisible chunks, then calculus might be an approximation that works well at large scales, but breaks down when applied to the fundamental structure of reality. This suggests that the Planck length might herald the need for entirely new mathematics to describe the deepest levels of physical reality. Just as quantum mechanics required the development of new mathematical tools that had no precedent in classical physics, understanding the physics of the Planck scale might require mathematical concepts that haven't yet been invented. The smooth functions and continuous symmetries that characterize current physics might give way to discrete structures and digital processes that operate according to rules we've never encountered. The absolute nature of the Planck length boundary also challenges our understanding of the relationship between mathematics and physical reality. In classical physics, mathematical concepts like points, lines, and smooth surfaces correspond directly to physical reality. A mathematical point has zero size, a line has zero thickness, and curves can be indefinitely smooth. But if the Planck length represents a fundamental granularity in space itself, then these mathematical idealization might not correspond to anything real in the physical universe. This suggests a profound shift in how we think about the role of mathematics in describing nature. Rather than mathematics providing perfect descriptions of physical reality, it might provide useful approximations that work well at the scales we can observe, but break down when pushed to their logical extremes. The Planck length might be telling us that nature has built-in protection against the infinities and paradoxes that often arise when mathematical concepts are pushed to their limits. The recognition of the Planck length as an unbreakable rule thus represents more than just the discovery of a new physical constant. It marks a fundamental shift in our understanding of the relationship between the continuous mathematics we use to describe nature and the potentially discrete reality that underlies our observations. At this boundary, the familiar world of smooth spacetime gives way to something entirely new, a realm where space and time themselves might be quantized, where the rules of physics are written in a digital language we're only beginning to glimpse, and where the ultimate nature of reality reveals itself to be far stranger and more wonderful than our everyday experience could ever suggest. For more than a century, physicists have pursued one of the most ambitious goals in all of science: the discovery of a single unified theory that could explain every force, every particle, and every phenomenon in the universe. This quest for a theory of everything represents humanity's deepest attempt to understand the fundamental nature of reality, to find the single set of equations from which all the complexity and beauty of the cosmos emerges. Yet at the heart of this search lies a profound contradiction, a clash between two of our most successful theories that seems to tear at the very fabric of our understanding. On one side stands general relativity, Einstein's magnificent theory of gravity that describes space-time as a smooth, continuous fabric that curves in response to matter and energy. This theory has passed every experimental test, from predicting the precise orbit of Mercury to detecting gravitational waves from colliding black holes billions of light-years away. It paints a picture of the universe as an elegant geometric structure, where gravity isn't a force pulling objects together, but the curvature of space-time itself guiding matter along the shortest possible paths through the four-dimensional continuum of space and time. On the other side stands quantum mechanics, the theory that governs the microscopic realm of atoms and particles. This framework reveals a universe that is fundamentally probabilistic rather than deterministic, where particles exist in multiple states simultaneously until observed, where the act of measurement creates reality rather than simply revealing it, and where empty space seethes with virtual particles popping in and out of existence. Quantum mechanics has been tested to extraordinary precision, enabling technologies from lasers to computer chips while revealing the strange and counterintuitive nature of reality at its smallest scales. Both theories work magnificently within their respective domains, yet they seem to describe fundamentally incompatible universes. General relativity assumes space and time form a smooth continuum that can be divided infinitely without limit, while quantum mechanics suggests that at sufficiently small scales, this continuity breaks down and reality becomes grainy and uncertain. General relativity is deterministic, allowing precise predictions of how objects will move through curved space-time, while quantum mechanics is inherently probabilistic, dealing in likelihoods and uncertainties rather than definite outcomes. The conflict between these two pillars of modern physics becomes most acute at extreme scales and energies, precisely the conditions that existed in the earliest moments after the Big Bang and that exist today in the hearts of black holes and at the Planck scale. When you try to apply both theories simultaneously to these extreme conditions, the mathematics breaks down catastrophically, yielding infinite results that have no physical meaning. The smooth spacetime of general relativity cannot accommodate the quantum fluctuations that quantum mechanics demands, while the probabilistic nature of quantum mechanics cannot be reconciled with the geometric certainty of curved spacetime. This mathematical crisis points to a fundamental incompleteness in our current understanding of physics. Neither theory alone can describe the full range of physical phenomena, yet combining them leads to contradictions and paradoxes that suggest both theories are approximations to some deeper truth. The search for this deeper truth has driven theoretical physics for decades, inspiring bold new approaches and radical reconceptualizations of the nature of space, time, and matter. The Planck length emerges as a crucial clue in this quest for unification. At this scale, quantum effects and gravitational effects become equally important, creating the very conditions where general relativity and quantum mechanics must be unified or replaced by something entirely new. The Planck length marks the boundary where both theories reach their limits simultaneously, where the smooth spacetime of relativity encounters the quantum foam of microscopic physics, where the deterministic curves of geometric gravity meet the probabilistic fluctuations of quantum fields. This convergence suggests that the Planck scale might be the natural arena for discovering the unified theory that has eluded physicists for so long. Any theory that successfully merges quantum mechanics and general relativity must make specific predictions about what happens at the Planck scale, about the structure of space and time at this fundamental boundary. The theory of everything, when it is finally discovered, will likely reveal the Planck length not as an arbitrary limit, but as a natural consequence of deeper principles that govern the universe at its most fundamental level. String theory represents one of the most ambitious attempts to achieve this unification. In this framework, the point particles of conventional physics are replaced by tiny, vibrating strings whose different modes of vibration correspond to different particles and forces. The theory naturally incorporates both quantum mechanics and general relativity, suggesting that gravity emerges from the geometric properties of extraspatial dimensions that are compactified at the Planck scale. In string theory, the Planck length becomes the natural scale of these fundamental strings, the size at which the underlying structure of matter and spacetime reveals itself. Other approaches to unification take different paths, but often converge on the same fundamental insight, that space and time themselves might not be fundamental features of reality, but emergent properties that arise from deeper, more basic constituents. Loop quantum gravity suggests that space-time is woven from discrete loops at the Planck scale, creating a quantum geometry that gives rise to the smooth continuum we observe at larger scales. Causal set theory proposes that space-time emerges from the relationships between discrete events, with the Planck scale marking the resolution of this underlying causal structure. These diverse approaches share a common recognition that the Planck length likely marks the scale where our current concepts of space and time break down and something entirely new takes over. The quest for a theory of everything is ultimately a quest to understand what lies beyond this boundary, to discover the deeper principles from which the familiar world of continuous space-time and classical matter emerges. In this search, the Planck length serves not as an obstacle, but as a guide, pointing toward the scale where the universe reveals its deepest secrets and where the long-sought unity of physics might finally be found. The discovery of this unified theory would represent more than just an intellectual achievement. It would fundamentally transform our understanding of what it means for anything to exist at all. Gravity stands apart from all other forces in the universe as something fundamentally different, almost mysterious in its unique characteristics. While the electromagnetic force can be shielded by conducting materials, while the strong nuclear force operates only within atomic nuclei, and while the weak nuclear force governs certain forms of radioactive decay, gravity seems to permeate every corner of existence without exception. It cannot be blocked, cannot be turned off, and affects every particle of matter and every photon of light with perfect impartiality. Yet for all its universality, gravity remains the most poorly understood of the fundamental forces, particularly when we attempt to describe it at the quantum level. The three other fundamental forces have been successfully integrated into the quantum mechanical framework through a mathematical structure known as the Standard Model of Particle Physics. Each of these forces operates through the exchange of specific particles. Photons carry the electromagnetic force. Gluons bind quarks together through the strong force, and W and Z bosons mediate the weak nuclear interactions that govern certain types of radioactive decay. These quantum field theories describe forces as arising from the continuous creation and annihilation of virtual particles that carry energy and momentum between interacting objects. This quantum description has proven extraordinarily successful. The electromagnetic force, when described quantum mechanically as quantum electrodynamics, makes predictions that match experimental observations to more than 10 decimal places, making it one of the most precisely tested theories in all of science. The strong and weak forces, unified with electromagnetism in the Standard Model, successfully predict the behavior of particles in high-energy collisions and explain the nuclear processes that power stars and create the elements. But gravity refuses to fit into this quantum mechanical framework. Unlike the other forces, gravity doesn't seem to operate through the exchange of particles in the conventional sense. Instead, it manifests as the curvature of space-time itself, bending the paths that objects follow through space and time. This geometric interpretation of gravity, Einstein's great insight, works magnificently at large scales, but creates profound problems when physicists try to apply quantum mechanical principles to gravitational phenomena. The fundamental difficulty arises from the nature of quantum mechanics itself. Quantum theory is built on the idea that physical quantities can be measured with arbitrary precision, limited only by the uncertainty principle, and that particles and fields exist within a fixed background of space and time. But gravity, as described by general relativity, tells us that space and time themselves are dynamic, changing in response to the presence of matter and energy. How can you apply quantum mechanics to a system where the very stage upon which quantum processes play out is itself subject to quantum fluctuations? This problem becomes acute at the Planck scale, where quantum effects and gravitational effects become equally important. At these tiny distances, the uncertainty principle demands that the geometry of space-time itself must be subject to quantum fluctuations. The smooth, well-defined curvature that characterizes general relativity gives way to a chaotic foam of quantum geometry where the very concepts of distance and time lose their familiar meaning. Virtual particles pop in and out of existence with such energy that they create microscopic black holes that appear and disappear faster than light can cross them. Attempts to construct a quantum theory of gravity using the same mathematical techniques that work for other forces run into immediate problems. When physicists try to calculate the quantum corrections to gravitational interactions, the mathematics yields infinite results that cannot be removed through the standard techniques of renormalization that work for electromagnetic and nuclear forces. These infinities aren't just technical inconveniences, they represent a fundamental breakdown in our ability to describe gravitational phenomena at the quantum level. The source of these infinities lies in gravity's unique relationship to energy and momentum. In quantum field theory, virtual particles of arbitrarily high energy contribute to physical processes. For the electromagnetic and nuclear forces, these high-energy contributions can be mathematically controlled and absorbed into the measured values of physical constants. But gravity couples to all forms of energy and momentum without discrimination, including the energy and momentum of virtual particles themselves. This creates a feedback loop where virtual particles generate gravitational effects that create more virtual particles, leading to a cascade of ever-increasing energy that renders the mathematics meaningless. This mathematical crisis points to a profound conceptual problem. The successful quantum field theories of the other forces all operate within a fixed background spacetime, treating space and time as unchanging stage upon which particles interact. But gravity is spacetime, the dynamic arena that responds to and shapes all other physical processes. Quantizing gravity means quantizing the very foundation upon which quantum mechanics itself is built, creating a conceptual puzzle that has resisted solution for decades. The Planck length emerges naturally from this crisis as the scale where these problems become unavoidable. At distances comparable to the Planck length, the gravitational effects of quantum fluctuations become so strong that they dominate the physics. Virtual particles carry enough energy to significantly curve space-time, while the uncertainty in the geometry of space itself becomes comparable to the distances being measured. This is the realm where any successful theory of quantum gravity must make definite predictions, where the smooth spacetime of general relativity must give way to some new description that incorporates both quantum uncertainty and gravitational dynamics. Various approaches to quantum gravity offer different solutions to this puzzle. String theory suggests that gravitons, the hypothetical particles that carry gravitational force, are vibrating strings rather than point particles, naturally regulating the infinities that plague conventional approaches. Loop quantum gravity proposes that space itself is woven from discrete quantum loops at the Planck scale, creating a quantum geometry that gives rise to smooth spacetime only as an approximation at larger scales. Each of these approaches makes specific predictions about the behavior of gravity at the Planck scale, about the ultimate structure of space and time, and about the fundamental nature of gravitational phenomena. The resolution of the quantum gravity problem will not only complete our understanding of the fundamental forces, but will likely reveal entirely new aspects of reality that operate at the boundary between the quantum and the cosmic, where the Planck length marks the transition from the familiar world of classical spacetime to the strange quantum realm that underlies all existence. The smooth, continuous fabric of spacetime that Einstein revealed to us represents one of the most beautiful and successful descriptions of reality ever conceived by human thought. For more than a century, this elegant geometric vision has guided our understanding of gravity, cosmology, and the large-scale structure of the universe. In Einstein's framework, space-time forms a four-dimensional manifold that curves gracefully around massive objects, creating the phenomenon we experience as gravitational attraction. This curvature flows smoothly from point to point, creating gentle gradients that guide the motion of everything from photons to planets along the shortest possible paths through the curved geometry of space and time. The mathematical elegance of this description rests on the assumption that space-time possesses infinite divisibility, that you can always zoom into smaller and smaller regions and find the same smooth, continuous structure at every scale. The calculus that Einstein used to formulate his field equations assumes that space and time can be divided into arbitrarily small intervals, that derivatives and integrals can be taken with perfect precision, and that the geometry of spacetime remains well defined no matter how closely you examine it. This mathematical smoothness enables general relativity to make remarkably precise predictions about phenomena ranging from the precession of planetary orbits to the emission of gravitational waves from distant cosmic collisions. But as we push our understanding towards smaller and smaller scales, this picture of smooth spacetime begins to encounter fundamental challenges that strike at the very heart of the geometric vision. The smooth manifold of general relativity, when examined through the lens of quantum mechanics, reveals itself to be an approximation that works magnificently at large scales, but breaks down catastrophically when applied to the microscopic realm where quantum effects dominate physical processes. The first cracks in the smooth spacetime picture appear when we consider the energy requirements for examining the geometry of space at increasingly fine scales. To probe the curvature of spacetime at a particular resolution, we need to send test particles or photons into that region and observe how they respond to the gravitational field. But as we attempt to examine smaller and smaller regions, the energy required for these measurements grows enormous, and this energy itself begins to contribute significantly to the gravitational field we're trying to measure. This creates a fundamental feedback loop that undermines the very concept of smooth spacetime at small scales. The act of measurement changes the quantity being measured, but unlike similar effects in other quantum systems, this change occurs through the gravitational field itself. The energy concentrated in a small region to probe its geometry creates additional curvature in spacetime, distorting the measurement and making it impossible to determine the true geometry independent of the measurement process. As we approach the Planck scale, this feedback becomes so severe that it completely destroys the concept of smooth spacetime. The energy required to probe the geometry at the Planck length is so enormous that it creates such extreme curvature in spacetime that the measurement process collapses into a black hole. The event horizon of this microscopic black hole encompasses the very region we're trying to measure, making it impossible to extract any information about the geometry within. But the breakdown of smooth spacetime involves more than just measurement problems. Quantum mechanics introduces a fundamental uncertainty into the geometry of space and time themselves. Just as particles in quantum systems exist in superpositions of multiple states until measured, the geometry of spacetime at the Planck scale may exist in superpositions of multiple configurations simultaneously. The sharp, well-defined curvature that characterizes classical general relativity gives way to a probabilistic description where spacetime geometry fluctuates quantum mechanically. These quantum fluctuations in the geometry of spacetime create what physicists call spacetime foam, a seething, chaotic realm where the smooth manifold of classical physics dissolves into something far more turbulent and unpredictable. In this foam, the familiar concepts of distance and duration become fuzzy and uncertain. A path through space might have multiple lengths simultaneously, depending on the quantum fluctuations in the geometry. The flow of time itself becomes irregular, speeding up and slowing down according to the probabilistic laws of quantum mechanics rather than the smooth universal progression that characterizes macroscopic physics. The transition from smooth spacetime to quantum geometry represents one of the most profound conceptual challenges in modern physics. It suggests that the continuous, deterministic picture of spacetime that works so well at observable scales is fundamentally incomplete. At the deepest level, space and time may not be the smooth, infinitely divisible continuum that our mathematical tools assume, but rather something more like a quantum entity that obeys the same probabilistic laws that govern particles and fields. This quantum nature of spacetime has profound implications for our understanding of causality and the flow of information through the universe. In classical general relativity, cause and effect propagate along well-defined paths through curved spacetime at speeds no greater than the speed of light. But in quantum spacetime, these causal relationships become uncertain and probabilistic. The clear distinction between past and future, between cause and effect, begins to blur in the quantum foam where space-time geometry fluctuates rapidly and unpredictably. The recognition that space-time itself must be treated as a quantum entity forces us to reconsider the most basic assumptions about the nature of reality. The stage upon which all physical processes play out may itself be subject to the strange and counterintuitive laws of quantum mechanics. Space and time, rather than providing a fixed background for quantum phenomena, may be quantum phenomena themselves, emerging from even more fundamental processes that operate according to rules we have yet to discover. At the Planck scale, where smooth spacetime gives way to quantum geometry, we approach the boundary between the known and the unknowable, where the familiar world of continuous space and time dissolves into something entirely new and mysterious. What lies beyond the boundary of the Planck length represents one of the most profound mysteries in all of physics, a question that pushes the very concept of physical reality to its breaking point. When we ask what happens to objects or structures smaller than 1.6 times 10 to the negative 35th meters, we're not simply asking about very tiny things that our current instruments cannot detect. We're asking whether the fundamental concepts of size, distance, and spatial extent have any meaning whatsoever at these scales, whether the universe possesses a built-in limit beyond which our most basic notions of physical existence simply cease to apply. Traditional physics offers us no guidance in this realm. The mathematical framework that describes everything from planetary motions to quantum interactions breaks down completely when pushed beyond the Planck scale. The equations of general relativity yield infinite curvatures and meaningless results, while quantum mechanics produces probability amplitudes that have no physical interpretation. The smooth functions and well-behaved mathematics that work so magnificently at observable scales transform into mathematical chaos when extended to distances smaller than the Planck length. This breakdown isn't merely a technical problem that might be solved with better mathematical tools or more sophisticated theories. It appears to represent a fundamental limit built into the structure of reality itself. The Planck length emerges naturally from the most basic constants of nature, the speed of light, Planck's constant, and the gravitational constant, suggesting that this limit isn't arbitrary, but reflects something deep about how the universe is constructed at its most fundamental level. The impossibility of probing sub-Planck distances stems from a fundamental principle that combines quantum mechanics with general relativity in a way that creates an absolute barrier to measurement. To examine any distance, you must use particles or photons with enough energy to resolve that scale. But as you attempt to probe smaller and smaller distances, the energy requirements grow catastrophically large. Eventually, you reach a point where the energy needed to make the measurement is so enormous that it curves space-time so severely that it creates a black hole whose event horizon encompasses the very region you're trying to examine. This isn't simply a practical limitation of our measuring devices, it's a fundamental constraint imposed by the laws of physics themselves. The energy required to probe the Planck scale is so large that it fundamentally alters the nature of space and time in the region being examined. The measurement destroys what it seeks to measure, not through crude experimental techniques, but through the inexorable operation of physical law. The universe seems to have built-in protection against being examined too closely, a cosmic privacy screen that operates at the deepest level of reality. But what does this mean for the concept of objects or structures that might theoretically be smaller than the Planck length? If such things could exist, they would inhabit a realm completely disconnected from the observable universe. No information could travel from these sub-Planck structures to the larger world, because any attempt to extract such information would require energies so enormous that they would create gravitational barriers that prevent the information from escaping. This isolation suggests that sub-Planck phenomena, if they exist at all, would be fundamentally unknowable and irrelevant to everything that happens at observable scales. They would be forever quarantined from the rest of reality by the energy requirements for interaction. In a very real sense, asking what happens below the Planck length might be like asking what happens outside the observable universe. The question might have an answer, but that answer could never influence or inform anything within our physical experience. The implications extend beyond mere measurement problems to challenge the very concepts of space and time themselves. If the Planck length represents a fundamental grain size for space, then distances smaller than this limit might simply not exist in any meaningful sense. Space itself might be quantized, composed of discrete indivisible units, each exactly one Planck length across. In this view, asking about sub-Planck distances would be like asking about fractional pixels in a digital image. The question assumes a continuity that doesn't actually exist in the underlying structure. This quantization of space would mean that the universe operates more like a vast three-dimensional grid than the smooth continuum that classical physics describes. Objects couldn't be positioned with arbitrary precision, but would be restricted to specific locations on this cosmic lattice. Motion wouldn't be perfectly continuous, but would occur in discrete jumps from one grid point to another, creating the illusion of smooth movement only when averaged over many quantum steps. Time, too, might be quantized at the Planck scale. The smallest meaningful interval of time would be the Planck time, approximately 5.4 times 10 to the negative 44 seconds, the time it takes light to travel one Planck length. Events couldn't be timed with precision greater than this fundamental temporal grain. The smooth flow of time that characterizes our macroscopic experience would emerge from the rapid succession of discrete temporal moments, like the illusion of motion created by a sequence of still frames in a movie. If both space and time are quantized at the Planck scale, then the universe would be fundamentally digital rather than analog. All physical processes would ultimately reduce to discrete operations on a cosmic computational grid, with the continuous equations of classical physics representing approximations that work well when averaged over many quantum cells, but break down when applied to individual grid points. This digital universe would possess a fundamental information processing capacity limited by the number of grid cells and the rate at which they can change state. The universe would be like a vast computer whose computational power is determined by the Planck scale parameters. Physical processes would be computations, and the evolution of the cosmos would represent the execution of a cosmic algorithm whose rules are written in the quantum mechanical laws that govern the behavior of each cell in the space-time grid. Below the Planck length, these questions lose their meaning entirely. There would be no below because space itself would be quantized. The concepts of smaller distances, shorter times, and finer details would be as meaningless as asking for a decimal expansion of infinity. The Planck scale would represent not just a practical limit, but an absolute boundary beyond which the familiar concepts of physics simply don't apply. The breakdown of conventional physics at the Planck scale has inspired some of the most radical and imaginative theoretical frameworks ever conceived by human thought. These theories venture far beyond the familiar territory of particles and forces to explore the possibility that space and time themselves might not be fundamental features of reality, but rather emergent phenomena that arise from deeper, more basic structures. In these bold new approaches to understanding the cosmos, the Planck length serves not as an ultimate barrier, but as a signpost pointing toward entirely new ways of thinking about the nature of existence. One of the most intriguing possibilities is that space-time itself emerges from the quantum mechanical phenomenon of entanglement, the mysterious connection that can link particles across vast distances. In this view, the smooth fabric of space-time that we observe at macroscopic scales would be woven from countless quantum entanglements operating at the Planck scale. Each tiny region of space would be connected to its neighbors through quantum correlations so complex and numerous that they create the illusion of continuous geometry when viewed from larger scales. This emergent spacetime would operate like a vast quantum network where information flows between nodes according to the rules of quantum mechanics rather than classical geometry. The distances we measure between objects would reflect the strength and pattern of quantum entanglements rather than motion through pre-existing space. Gravity itself might emerge from changes in this entanglement structure, with massive objects creating distortions in the quantum network that we experience as curved space-time. The mathematical framework for this emergent geometry suggests that space and time don't exist at the Planck scale in any form we would recognize. Instead, there would be a quantum information structure that processes and stores data about the relationships between events. This structure would operate according to rules that have no counterpart in classical physics, creating patterns of correlation and information flow that give rise to the familiar 3 dimensions of space and 1 dimension of time, only when averaged over enormous numbers of quantum operations. Another revolutionary approach suggests that space-time emerges from quantum error correction, the same principle that protects quantum information in quantum computers. In this framework, the universe operates like a vast quantum computer that continuously corrects errors in its own information processing. The stable, persistent reality we observe would be the result of this cosmic error correction system maintaining coherent information despite the constant quantum fluctuations that threaten to destroy it. The Planck scale would represent the fundamental scale of this quantum error correction process. Below this scale, quantum errors would accumulate faster than they could be corrected, leading to the breakdown of stable information processing and the dissolution of space and time themselves. Above this scale, the error correction would be so effective that it creates the illusion of smooth, continuous space-time that classical physics describes. This quantum computational view of reality suggests that physical laws aren't fundamental truths about the universe, but rather algorithms that the cosmic computer uses to process information. The constants of nature would be parameters in these algorithms, and the evolution of the universe would represent the execution of a vast computational process whose complexity far exceeds anything we can currently imagine. Some theoretical frameworks go even further, proposing that reality emerges from pure mathematics without any physical substrate whatsoever. In these approaches, the universe would be a mathematical structure that exists in the realm of abstract possibility, with physical reality corresponding to the patterns of information that can exist consistently within this mathematical framework. Space and time would be dimensions within this abstract mathematical space, and the Planck scale would represent the finest resolution at which mathematical patterns can maintain their coherence. This mathematical universe hypothesis suggests that asking what exists beyond the Planck scale is like asking what exists beyond the boundaries of a mathematical theorem. The question assumes a physical context that doesn't actually apply to the underlying reality. The Planck length would mark the limit of mathematical consistency rather than a physical barrier, beyond which the patterns that constitute reality lose their logical coherence and dissolve into mathematical contradiction. Yet another approach explores the possibility that our familiar 3-dimensional space is actually a holographic projection of information encoded on a 2-dimensional surface. In this holographic principle, all the information that appears to exist within a volume of space is actually stored on the boundary of that volume, much like a hologram encodes 3-dimensional information on a 2-dimensional surface. The Planck scale would represent the pixel size of this cosmic hologram, the fundamental unit of information that creates the illusion of 3-dimensional reality. The holographic universe would mean that the depth and volume we perceive in space are emergent properties of information processing rather than fundamental features of reality. The laws of physics would be rules for how information on the holographic surface creates the appearance of particles and forces moving through three-dimensional space. Gravity, in particular, would emerge from the way information is organized and processed on this cosmic boundary. These theoretical frameworks share a common recognition that the current limits of physics at the Planck scale point towards something far more radical than simply discovering new particles or forces. They suggest that our entire conceptual framework for understanding reality, based on objects moving through space and time, may be fundamentally incomplete. The Planck length may be showing us that space, time, matter, and energy are all emergent phenomena arising from deeper information theoretic structures that operate according to principles we're only beginning to glimpse. The implications are staggering. If space-time itself emerges from quantum information processing, then the universe is far stranger and more wonderful than anything classical physics could have imagined. Reality would be more like a vast computation than a mechanical system, more like a pattern of information than a collection of objects, more like a mathematical theorem than a physical structure. The Planck scale would mark not the smallest distance in space, but the boundary between the familiar world of emergent classical reality and the alien realm of pure quantum information from which everything we know somehow arises. When you contemplate the Planck length from the perspective of cosmic architecture, you begin to appreciate how this impossibly tiny scale connects to the grandest structures and most fundamental patterns that govern the entire universe. The same mathematical relationships that define the Planck length as the smallest meaningful distance also appear in the equations that describe the birth of galaxies, the expansion of space itself, and the deep symmetries that organize reality at every scale from the quantum to the cosmic. This connection between the infinitesimally small and the incomprehensibly large reveals something profound about the nature of cosmic design. The universe appears to be constructed according to principles that operate consistently across all scales, creating patterns and relationships that echo from the Planck scale to the scale of galaxy clusters spanning hundreds of millions of light years. The same fundamental constants that determine the Planck length, the speed of light, Planck's constant, and Newton's gravitational constant also determine the rate of cosmic expansion, the formation of the first stars, and the large-scale structure that emerged from quantum fluctuations in the primordial universe. Consider how the Planck scale connects to the earliest moments of cosmic history. In the first fraction of a second after the Big Bang, when the universe was smaller than an atom and hotter than the core of any star, quantum fluctuations at the Planck scale may have seeded the density variations that eventually grew into the cosmic web of galaxies and galaxy clusters we observe today. These tiny quantum fluctuations, operating at scales where space and time themselves become uncertain, somehow contained the blueprint for the vast structures that would emerge billions of years later. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, carries the imprint of these primordial quantum fluctuations. When we observe the tiny temperature variations in this ancient light, we're seeing the consequences of processes that occurred at the Planck scale in the universe's first moments. The largest structures in the cosmos trace their origin to the smallest meaningful fluctuations that quantum mechanics allows, creating a direct connection between the Planck length and the scale of the observable universe itself. This relationship suggests that the universe possesses a kind of fractal architecture, where patterns established at the smallest scales propagate upward to influence structures at every larger scale. The quantization of space and time at the Planck scale may create discrete patterns that influence the formation of atoms, the behavior of molecules, the evolution of stars, and ultimately the large-scale structure of space-time itself. Each level of reality reflects and amplifies the patterns established at the fundamental Planck scale. The Planck length also provides a natural unit for measuring the most extreme environments in the universe. Black holes, those regions where gravity becomes so strong that not even light can escape, have event horizons whose areas are quantized in units related to the Planck length. The entropy of a black hole, which measures the amount of information it contains, is proportional to the area of its event horizon, measured in units of the Planck length squared. This connection between the quantum scale and the cosmic scale suggests that black holes serve as bridges between the microscopic quantum world and the macroscopic realm of curved space-time. The information paradox of black holes, the question of what happens to information that falls into a black hole, may ultimately be resolved by understanding physics at the Planck scale. If space-time itself is quantized at this scale, then black holes might not destroy information, but rather encode it in quantum patterns at the Planck scale that somehow preserve all the details of what fell in. The resolution of this paradox would require a deep understanding of how quantum information is processed at the fundamental scale of space and time. The cosmic expansion itself may be intimately connected to processes operating at the Planck scale. Some theories suggest that the expansion of space occurs through the continuous creation of new units of space at the Planck scale, with each cubic Planck length of space somehow multiplying and creating the illusion that objects are moving apart, when in reality space itself is proliferating. This would mean that the largest scale phenomenon we can observe, the expansion of the entire universe, results from processes occurring at the smallest possible scale. The constants of nature that determine the Planck length also determine the fundamental parameters that allowed complexity to emerge in the universe. The strength of gravity, the mass of fundamental particles, and the rate of cosmic expansion are all finely tuned to values that permit the formation of stars, planets, and ultimately the complex chemistry that enables life. This cosmic fine-tuning may reflect deep principles that operate at the Planck scale, where the fundamental parameters of reality are somehow encoded in the quantum geometric structure of space and time. The interconnectedness revealed by the Planck scale extends to the very possibility of consciousness and observation. The fact that we can contemplate the Planck length at all depends on a vast cosmic conspiracy that began with quantum fluctuations at the smallest scales and eventually produced stars, planets, biological evolution, and thinking beings capable of discovering the mathematical relationships that govern reality. The Planck scale thus connects not only the smallest and largest features of the physical universe, but also bridges the gap between objective physical law and subjective conscious experience. This grand design suggests that the universe is not a collection of separate phenomena operating at different scales, but rather a unified system where every level of reality reflects and influences every other level. The Planck length serves as a fundamental organizing principle that connects quantum mechanics to cosmology, microscopic fluctuations to galactic structure, and the abstract mathematics of theoretical physics to the concrete reality of our existence within the cosmic order. In contemplating this tiny distance, we glimpse the deep unity that underlies the apparent diversity of natural phenomena, revealing a universe whose architecture reflects the same elegant mathematical principles from the smallest possible scales to the grandest cosmic vistas. The human quest to understand the Planck length represents far more than an abstract mathematical exercise or a curiosity for theoretical physicists. It embodies one of the most profound intellectual journeys our species has ever undertaken, the search for meaning in the deepest structures of reality itself. When you contemplate this impossibly tiny distance, you're participating in a tradition that stretches back to the earliest human attempts to comprehend the nature of existence, to find pattern and purpose in the apparent chaos of natural phenomena, and to locate humanity's place within the vast cosmic order. This search for understanding begins with a fundamental recognition that has driven human inquiry since our ancestors first looked up at the night sky and wondered about their place in the cosmos. We are finite beings attempting to grasp infinite mysteries, creatures whose existence spans mere decades, trying to comprehend processes that unfold over billions of years. Minds evolved to navigate the middle-scale world of everyday experience, now pushing toward the absolute limits of what can be known about the structure of reality. The discovery of the Planck length forces us to confront profound questions about the nature of knowledge itself. What does it mean to understand something that cannot be directly observed, measured, or experienced? How can we claim knowledge about scales so far removed from human experience that they challenge the very concepts we use to describe reality? The Planck scale exists at the boundary between the known and the unknowable, where mathematical inference and theoretical speculation must substitute for direct observation and empirical measurement. This limitation reveals something deeply humbling about the human condition. Despite our remarkable success in uncovering the laws of physics, mapping the structure of the universe, and predicting the behavior of natural systems across vast ranges of scale and complexity, we remain fundamentally constrained by the nature of physical law itself. The universe appears to have built-in limits on what can be known, boundaries beyond which even the most sophisticated theories and the most precise measurements cannot penetrate. Yet these limitations also reveal something extraordinary about human consciousness and our capacity for abstract reasoning. The fact that we can conceive of the Planck length at all, that we can perform mathematical calculations that reveal its existence and significance, demonstrates a remarkable feature of conscious minds. Our ability to transcend the immediate boundaries of sensory experience and discover truths about reality that lie far beyond the reach of direct observation. The mathematical relationships that define the Planck length emerge from pure thought, from the logical manipulation of abstract symbols according to rules that seem to reflect deep patterns in the structure of the universe. This connection between human mathematical reasoning and the fundamental architecture of reality suggests something profound about the relationship between consciousness and cosmos, between the patterns of thought and the patterns that organize physical existence. The search for meaning at the quantum scale also reflects a distinctly human need to find coherence and purpose in our understanding of the world. We are not content simply to catalogue phenomena or memorize equations. We seek to understand how everything fits together, how the smallest scales connect to the largest, how the mathematical abstractions of theoretical physics relate to the concrete reality of our lived experience. The Planck length serves as a focal point for these deeper questions about unity and meaning in the physical universe. This quest for understanding reveals both the power and the limits of scientific knowledge. Science has shown us that the universe operates according to mathematical principles that can be discovered through careful observation and logical reasoning. We have learned to predict eclipses, to split atoms, to detect gravitational waves from colliding black holes billions of light years away, and to trace the history of the cosmos back to its first moments. Yet the same scientific understanding that reveals these remarkable truths also reveals the boundaries of what can be known. The Planck length stands as a testament to both human intellectual achievement and human intellectual humility. It represents the furthest reach of our current understanding, while simultaneously marking the boundary beyond which that understanding necessarily fails. It demonstrates our capacity to discover deep truths about the nature of reality, while reminding us that some aspects of existence may remain forever beyond our comprehension. This recognition of limits need not diminish our sense of wonder or our motivation to continue exploring. Instead, it can deepen our appreciation for the mysterious nature of existence and our remarkable fortune to be conscious beings capable of contemplating these profound questions. The fact that the universe has evolved conscious observers capable of discovering the Planck length, of recognizing its significance, and of pondering its implications represents one of the most extraordinary developments in the history of the cosmos. The search for meaning in quantum mechanics and cosmology also connects us to the broader human tradition of seeking purpose and significance in our existence. The same impulse that drives us to create art, to tell stories, to build civilizations, and to care for one another also drives us to probe the deepest mysteries of physical reality. The quest to understand the Planck length is, at its heart, a quest to understand ourselves and our place in the cosmic order. In recognizing that the universe contains fundamental mysteries that may remain forever beyond human understanding, we also recognize that our capacity to discover and contemplate these mysteries is itself one of the most remarkable features of the cosmos. The existence of conscious beings capable of mathematical reasoning and scientific discovery may be as profound a mystery as any revealed by our investigations of the quantum realm. The fact that matter organized in the particular pattern of human brains can contemplate the Planck length represents an extraordinary emergence of complexity and consciousness from the fundamental physical processes that govern the universe at its smallest scales. When you consider your place in the universe from the perspective of the Planck length, the result is both humbling and extraordinary. You exist at a scale that is roughly halfway between the Planck length and the size of the observable universe, occupying a middle realm that spans about 30 orders of magnitude in each direction. This positioning places you at a unique vantage point in the cosmic hierarchy of scales, large enough to contemplate the quantum realm, yet small enough to comprehend the vastness of space and time that surrounds you. Your physical body, composed of approximately 37 trillion cells, represents an intricate organization of matter that bridges multiple scales of reality. Each cell contains molecular machinery that operates according to quantum mechanical principles, yet these quantum processes are so precisely coordinated that they create the stable, predictable biological systems that sustain your consciousness and enable your capacity for thought. The quantum uncertainty that dominates at the Planck scale is somehow harnessed and organized by biological evolution to create the remarkable information processing system that is your brain. This emergence of consciousness from quantum processes represents one of the most profound mysteries in all of science. Your ability to contemplate the Planck length depends on neural networks composed of billions of individual neurons, each one a complex electrochemical system that processes and transmits information according to the laws of physics. Yet somehow, from this collection of physical processes emerges your subjective experience of understanding, your sense of wonder at the mysteries of the quantum realm, and your capacity to imagine scales of reality far beyond anything you can directly perceive. The relationship between your consciousness and the Planck scale reveals something remarkable about the nature of information in the universe. The patterns of neural activity that constitute your thoughts about quantum mechanics are themselves quantum mechanical processes, subject to the same fundamental laws that govern particle interactions at the smallest scales. When you think about the Planck length, you are, in a very real sense, using quantum processes to contemplate quantum processes, employing the quantum information processing capabilities of your brain to understand the quantum nature of reality itself. This self-referential quality of consciousness contemplating quantum mechanics suggests deep connections between mind and the fundamental structure of the universe. Some theories propose that consciousness itself may be intimately connected to quantum processes, that the subjective experience of awareness may emerge from quantum information processing in ways that classical physics cannot explain. If true, this would mean that your ability to understand the Planck length reflects a fundamental harmony between the structure of conscious minds and the quantum architecture of reality. Your temporal existence also provides a unique perspective on the relationship between human experience and the Planck scale. Your lifespan, measured in decades, encompasses roughly 10 to the 18th Planck times, an enormous number that reflects the vast difference between the timescales of human experience and the fundamental temporal intervals at which quantum processes occur. Every moment of your conscious experience contains countless quantum events, each one occurring at timescales so brief that billions upon billions of them unfold in the time it takes for a single thought to form in your mind. Yet despite this vast difference in temporal scales, your consciousness somehow integrates these quantum processes into coherent thoughts, memories, and experiences. The stability of your personal identity across years and decades emerges from quantum processes that fluctuate on timescales, trillions of times shorter than anything you can directly perceive. This integration of quantum processes into macroscopic consciousness represents one of the most remarkable examples of how complex, stable phenomena can emerge from the probabilistic quantum substrate of reality. The spatial scale of your existence also illuminates the relationship between human experience and the Planck length. Your brain, roughly the size of two closed fists, contains information processing capabilities that somehow enable you to contemplate distances 35 orders of magnitude smaller than an atom. This remarkable feat of abstraction demonstrates the extraordinary power of pattern recognition and mathematical reasoning that consciousness makes possible. Through pure thought, you can transcend the immediate boundaries of your physical existence and explore realms of reality that lie far beyond the reach of direct sensory experience. Your position in the cosmic scale hierarchy also provides insight into why the universe appears comprehensible to conscious beings like yourself. The middle scale realm you inhabit is characterized by the emergence of complexity and pattern from simpler quantum mechanical processes. At your scale, quantum uncertainty averages out to create the stable, predictable phenomena of classical physics, while the vast scales of cosmology remain accessible through mathematical inference and observational astronomy. This intermediate position may be essential for the development of consciousness and scientific understanding. The fact that beings at your scale can discover and contemplate the Planck length suggests something profound about the relationship between consciousness and cosmic evolution. The universe has evolved for nearly 14 billion years, creating conditions that allow matter to organize into complex patterns capable of self-reflection and scientific inquiry. Your existence represents an extraordinary development in the history of the cosmos, the emergence of conscious observers capable of understanding the mathematical relationships that govern reality at its deepest levels. This perspective transforms the apparent insignificance of human existence in the vast cosmos into something far more remarkable. While you may be tiny compared to galaxies and brief compared to cosmic timescales, you possess something that may be extraordinarily rare in the universe: the capacity for mathematical reasoning and scientific understanding that enables you to comprehend the Planck length and its implications for the nature of reality. Your consciousness represents a cosmic development of potentially profound significance, the emergence of the universe's capacity to understand itself. From the Planck scale perspective, your life represents an extraordinary opportunity to participate in one of the universe's most remarkable achievements: the development of conscious beings capable of discovering and contemplating the fundamental laws that govern existence. Your ability to understand the Planck length connects you directly to the deepest mysteries of reality, making you a participant in the cosmic process of self-discovery that has been unfolding since the first moments after the Big Bang. What does it truly mean for something to be small? This question, which might seem almost trivially simple, opens into one of the most profound philosophical puzzles that the Planck length forces us to confront. In your everyday experience, smallness is a relative concept. A grain of sand is small compared to a mountain. A bacterium is small compared to a grain of sand. An atom is small compared to a bacterium. Each level of smallness reveals new details and complexities that were invisible at larger scales, creating an apparently endless hierarchy of ever tinier structures and phenomena. But the Planck length challenges this intuitive understanding by suggesting that there may be an absolute limit to smallness itself, a boundary beyond which the very concept of smaller loses its meaning. This isn't simply a practical limitation imposed by the inadequacy of our measuring instruments or the current state of our theoretical understanding. It appears to be a fundamental constraint built into the structure of reality, a point at which the familiar concepts of size, distance, and spatial extent cease to apply. Consider how revolutionary this idea is. Throughout human history, the discovery of smaller and smaller structures has consistently revealed new levels of complexity and organization. The invention of the microscope revealed cells within living organisms. Advances in chemistry revealed atoms within molecules. Particle accelerators revealed quarks within protons and neutrons. Each new level of magnification opened vistas of previously unknown phenomena, suggesting that this process of discovery could continue indefinitely, limited only by the sophistication of our tools and theories. The Planck length suggests that this process has a natural endpoint, a scale beyond which there are no smaller structures to discover, because the very concept of spatial structure breaks down. At the Planck scale, space itself appears to become quantized, composed of discrete, indivisible units that cannot be further subdivided. This would mean that the universe operates more like a digital image, appearing smooth and continuous from a distance, but revealing its pixelated structure when examined at sufficient magnification. But what does it mean for space to be pixelated at the most fundamental level? The implications extend far beyond the technical details of quantum mechanics and cosmology to challenge our most basic assumptions about the nature of existence itself. If space comes in discrete units, then the smooth, continuous motion that characterizes your everyday experience would be revealed as an illusion created by rapid quantum jumps from one spatial pixel to another. The flowing analog world of classical physics would emerge as an approximation of an underlying digital reality operating at the Planck scale. This digitization of reality at the smallest scales suggests a profound shift in how we understand the relationship between mathematics and physical existence. The continuous functions and smooth curves that mathematicians have studied for centuries may not correspond to anything real in the physical universe. Instead, they may be useful approximations that work well at large scales, but break down when applied to the fundamental structure of space-time. The calculus that describes change and motion may be a powerful tool for understanding emergent phenomena without capturing the discrete quantum mechanical processes from which these phenomena arise. The concept of absolute smallness also forces us to reconsider the relationship between infinity and physical reality. Pure mathematics, any distance can be divided by 2, creating a smaller distance, and this process can be repeated without limit, generating an infinite sequence of ever smaller quantities. But if the Planck length represents a true minimum distance, then this mathematical process of infinite subdivision doesn't correspond to anything physically meaningful. The universe may be fundamentally finite in its spatial resolution, composed of a large but definite number of spatial pixels rather than the infinite continuum that mathematical analysis assumes. This limitation on smallness connects to deep questions about the nature of information and computation in the universe. If space is quantized at the Planck scale, then the universe possesses a finite information storage capacity determined by the number of Planck scale volumes and the number of different states each volume can assume. This would make the universe equivalent to a vast but finite computer, processing information about the quantum states of each spatial pixel according to the laws of physics. The philosophical implications of absolute smallness extend to questions about the nature of reality and existence. If there is a smallest meaningful distance, then the universe may be fundamentally discrete rather than continuous, more like a computational process than a mechanical system. Physical laws would be algorithms operating on discrete data rather than equations describing continuous functions. The evolution of the universe would be a cosmic calculation unfolding step by step according to quantum mechanical rules. This perspective transforms the Planck length from a technical detail of advanced physics into a fundamental principle that shapes our understanding of what it means for anything to exist. The boundary of smallness may be the boundary between being and non-being, between the realm of physical existence and the abstract mathematical concepts that we use to describe it. Beyond the Planck length, the question how small may be as meaningless as asking for the colour of the number 7 or the temperature of Thursday. The recognition that smallness may have an absolute limit also reveals something remarkable about human consciousness and its capacity for abstract reasoning. Despite being composed of matter organised at scales vastly larger than the Planck length, your mind can contemplate this ultimate boundary and recognise its significance for the nature of reality. Through pure mathematical reasoning, you can discover principles that operate at scales far beyond anything you could ever directly experience, revealing deep truths about the structure of existence that remain invisible to direct observation. In contemplating the absolute nature of the Planck length smallness, you encounter one of the most profound mysteries of existence: the relationship between the continuous, flowing experience of consciousness and the discrete, quantized reality from which it emerges. Your thoughts about smallness arise from quantum processes operating at the Planck scale, yet somehow transcend those processes to contemplate the fundamental nature of space and time themselves. When you step back to contemplate the full spectrum of existence, from the Planck length to the edge of the observable universe, you encounter one of the most profound paradoxes in all of human understanding: the relationship between the infinite and the infinitesimal. These two extremes of scale represent opposite boundaries of comprehension, yet they are intimately connected through the mathematical relationships that govern the structure of reality. The same physical constants that define the smallest meaningful distance also determine the largest possible structures. The same quantum mechanical principles that operate at the Planck scale also shape the formation of galaxies billions of light years across. The observable universe, stretching roughly 93 billion light years in diameter, contains everything that light has had time to reach us since the Big Bang began, 13.8 billion years ago. This cosmic horizon represents not just a boundary of observation, but a fundamental limit on what can be causally connected to our location in space and time. Beyond this boundary lies the realm of the truly infinite regions of space that may extend without limit, containing structures and phenomena that we can never observe or influence because the finite speed of light prevents any information from traversing such vast distances within the age of the universe. Yet this cosmic immensity emerges from processes that operate at the smallest possible scales. The quantum fluctuations that occurred at the Planck scale during the universe's first moments somehow contained the seeds for all the large-scale structure we observe today. The tiny variations in density that quantum mechanics demanded at the Planck scale grew over billions of years to become the cosmic web of galaxies, the vast filaments of dark matter, and the enormous voids that characterize the universe at its largest scales. This connection between the infinitesimal and the infinite reveals a deep principle about the nature of complexity in the cosmos. The universe appears to be organized as a vast hierarchy of structures, with each level emerging from the interactions of components at smaller scales. Galaxies form from the gravitational collapse of dark matter and gas. Stars condense from the gravitational instability of molecular clouds. Planets accrete from the collision and merger of smaller bodies, and life emerges from the complex chemistry of organic molecules. Yet all of these phenomena ultimately trace their origin to quantum mechanical processes operating at the Planck scale. The mathematical relationship between these extremes is encoded in the fundamental constants of nature. The same speed of light that defines the cosmic horizon also appears in the definition of the Planck length. The same gravitational constant that governs the expansion of the universe also determines the scale at which quantum gravity becomes important. The same quantum mechanical principles that create uncertainty at the Planck scale also drove the inflationary expansion that stretched the early universe to its current enormous size. This mathematical unity suggests that the universe possesses a kind of self-similarity across scales, where the same underlying principles manifest differently at different levels of organization. The probabilistic laws of quantum mechanics that govern individual particles somehow give rise to the statistical regularities that characterize large-scale cosmic structure. The discrete quantized processes that operate at the Planck scale somehow create the smooth, continuous spacetime that Einstein's general relativity describes at macroscopic scales. The existence of these two extremes also illuminates the remarkable nature of human consciousness and its place in the cosmic order. You exist at an intermediate scale that allows you to contemplate both the infinitely large and the infinitesimally small through the power of abstract reasoning and mathematical analysis. Your brain, composed of biological structures operating at molecular and cellular scales, can somehow process information about phenomena that span more than 60 orders of magnitude in size, from the Planck length to the cosmic horizon. This cognitive capacity represents one of the most extraordinary emergent properties in the known universe. The same quantum mechanical processes that operate at the Planck scale have somehow organized themselves, through billions of years of cosmic and biological evolution, into patterns complex enough to contemplate their own foundations. Consciousness emerges from quantum processes yet transcends them, using mathematical reasoning to discover truths about scales of reality far beyond anything that could be directly experienced by any biological organism. The relationship between infinite space and infinitesimal time also reveals deep connections between the structure of the universe and the nature of existence itself. If space extends infinitely beyond the cosmic horizon, then every possible arrangement of matter and energy may exist somewhere in the infinite expanse of the cosmos. This would mean that the processes occurring at the Planck scale, repeated across infinite space and infinite time, would generate every possible variation of cosmic structure and evolution. Yet the infinitesimal scale of the Planck length suggests that even infinite space may be composed of a finite amount of information, stored in discrete pixels of space-time, each no smaller than 1 Planck length across. This quantization of space would mean that infinity, when examined closely enough, reveals itself to be constructed from finite, discrete components. The smooth continuum of infinite space would emerge as an approximation of an underlying digital reality operating at the quantum scale. The contemplation of these extremes forces us to confront the limits of human experience and understanding. No conscious being could ever directly perceive the Planck scale or travel to the edge of the observable universe. These realms remain forever beyond the reach of direct experience, accessible only through the indirect methods of mathematical inference and theoretical reasoning. Yet through these methods, consciousness can transcend its biological limitations and discover deep truths about the nature of reality that operate far beyond the scales at which life and awareness are possible. In recognizing both the infinite vastness of space and the infinitesimal brevity of the Planck time, we encounter the fundamental mystery of existence itself. How does anything manage to exist at all within this vast hierarchy of scales? The answer may lie in the remarkable fact that the universe appears to be structured in such a way that complexity and consciousness can emerge from the interplay between these extremes, creating islands of order and awareness within the vast cosmic ocean of space and time. The discovery of the Planck length confronts us with one of the most profound questions in all of human intellectual history. Are there fundamental limits to what consciousness can know about the nature of reality? This question strikes at the heart of the scientific enterprise and challenges our deepest assumptions about the relationship between mind and cosmos, between the patterns of thought that arise in conscious beings and the mathematical structures that appear to govern the physical universe. For centuries, the progress of science has followed a pattern of pushing beyond apparent limits, of discovering new realms of knowledge that were previously thought to be forever beyond human understanding. When ancient astronomers struggled to comprehend the motion of the planets, Newton's laws revealed the mathematical principles that govern celestial mechanics. When the nature of light seemed impossibly mysterious, Maxwell's equations unified electricity, magnetism, and optics into a single theoretical framework. When the atom appeared to be indivisible, quantum mechanics revealed the rich internal structure of matter at the smallest scales. Each breakthrough suggested that human reason, armed with mathematical analysis and careful observation, could eventually penetrate any mystery and uncover the hidden principles that govern natural phenomena. The success of science in predicting eclipses, splitting atoms, detecting gravitational waves, and mapping the cosmic microwave background seemed to confirm that the universe is fundamentally comprehensible to conscious minds, capable of abstract reasoning and logical analysis. But the Planck length introduces a different kind of limit, one that appears to be built into the structure of physical law itself, rather than imposed by the limitations of current knowledge or technology. This isn't simply a boundary that might be crossed with better instruments or more sophisticated theories. It represents a scale at which the very concepts that science uses to describe reality, space, time, causality, measurement, appear to break down completely. The mathematical crisis that occurs at the Planck scale suggests that our most successful theories of physics are revealing their own boundaries. When we push the equations of quantum mechanics and general relativity to their logical extremes, they yield infinite results and mathematical contradictions that seem to indicate the breakdown of the theoretical frameworks themselves. This isn't a sign that our theories are wrong, but rather that they are incomplete, that they represent approximations to some deeper truth that operates according to principles we have yet to discover. This recognition of fundamental limits raises profound questions about the nature of scientific knowledge and its relationship to objective reality. If there are aspects of the universe that remain forever beyond the reach of observation and measurement, how can we claim to understand the true nature of existence? If the most fundamental scales of space and time operate according to principles that transcend our current mathematical frameworks, what does this tell us about the relationship between human reason and cosmic truth? The limits imposed by the Planck scale may reflect deeper constraints on the relationship between consciousness and physical reality. Conscious minds evolved within the middle-scale realm of classical physics, where objects have definite positions and velocities, where cause and effect follow predictable patterns, and where the passage of time creates a clear distinction between past and future. The quantum realm operates according to fundamentally different principles, where particles exist in superpositions of multiple states, where measurement creates rather than reveals reality, and where the very concepts of space and time become uncertain and probabilistic. The Planck scale may represent the absolute limit of this quantum strangeness, the boundary beyond which the concepts that conscious minds use to organize their understanding of reality lose all meaning. This would suggest that there are aspects of the universe that are not merely unknown, but fundamentally unknowable to beings like ourselves, whose patterns of thought are shaped by evolution within the classical realm of everyday experience. Yet this recognition of limits also reveals something extraordinary about the capacity of consciousness to transcend its evolutionary origins. Despite being composed of matter organized according to classical physics, human minds can contemplate quantum mechanics, can discover the Planck length through mathematical reasoning, and can recognize the significance of these discoveries for our understanding of reality. This suggests that consciousness possesses a remarkable capacity for abstraction that allows it to extend beyond the immediate boundaries of its physical substrate. The wonder that arises from contemplating these limits may be one of the most distinctively human responses to the mysteries of existence. Unlike other known forms of consciousness, human awareness seems uniquely capable of recognizing and appreciating the boundaries of its own understanding. We can feel awe at the vastness of the cosmos, humility in the face of quantum mechanical strangeness, and wonder at the mathematical elegance of physical law, even when these phenomena lie far beyond the reach of direct experience. This capacity for wonder in the face of the unknown may represent one of the most valuable aspects of human consciousness. Rather than being frustrated by the limits that the Planck scale reveals, we can appreciate the remarkable fact that finite minds can discover and contemplate infinite mysteries. The existence of boundaries to knowledge doesn't diminish the value of what we can know, but rather highlights the extraordinary nature of consciousness and its ability to push against those boundaries through mathematical reasoning and scientific inquiry. The beauty of confronting these unknowns lies not in the hope of eventually overcoming all limitations, but in the recognition that the universe contains mysteries deep enough to inspire wonder and profound enough to humble even our most sophisticated theoretical frameworks. The Planck length stands as a testament to both the power and the limits of human understanding, marking a boundary where known physics ends and genuine mystery begins. In acknowledging these limits, we don't abandon the scientific quest for understanding, but rather gain a deeper appreciation for the remarkable achievements that consciousness has already accomplished in discovering the mathematical principles that govern reality, from the smallest observable scales to the largest cosmic structures. The wonder that emerges from this recognition may be one of consciousness's greatest gifts, the ability to find meaning and beauty in contemplating the very boundaries of what can be known. As our exploration of the Planck length draws toward its conclusion, we find ourselves confronting a truth that transforms our understanding of existence itself. This impossibly tiny distance, 1.6 times 10 to the negative 35th meters, has revealed itself to be far more than simply the smallest measurement in physics. It stands as a fundamental boundary that forces us to reconsider the very nature of space, time, and reality, challenging our deepest assumptions about the cosmos and our place within it. The Planck length compels us to recognize that the universe operates according to principles far stranger and more wonderful than our everyday experience could ever suggest. The smooth, continuous spacetime that forms the backdrop of our daily lives emerges as an approximation, a useful illusion that works magnificently at the scales we can observe, but breaks down completely when pushed to its logical limits. Beneath the familiar world of classical physics lies something far more mysterious, a realm where space itself may be quantized into discrete pixels, where time flows in discontinuous jumps, and where the very concepts of distance and duration lose their familiar meaning. This recognition brings with it a profound sense of cosmic humility. Despite our remarkable success in mapping the universe from the scale of subatomic particles to the cosmic web of galaxies, we find ourselves confronted by a boundary beyond which our most sophisticated theories simply cannot penetrate. The Planck scale marks the frontier where known physics ends and genuine mystery begins, where the mathematical tools that have served us so well in understanding the natural world reveal their own limitations and point toward deeper truths that remain beyond our current comprehension. Yet this humility is accompanied by an even more profound sense of wonder at the extraordinary nature of consciousness and its capacity for abstract reasoning. The fact that beings like ourselves, composed of matter, organized at scales vastly larger than the Planck length, can discover and contemplate this fundamental boundary represents one of the most remarkable achievements in the history of the cosmos. Through pure mathematical reasoning, we have pushed our understanding to the very limits of what appears to be knowable, revealing principles that operate at scales so far removed from human experience that they challenge the foundations of our conceptual frameworks. The implications of the Planck length extend far beyond the technical details of quantum mechanics and cosmology to transform our understanding of what it means for anything to exist at all. If space and time themselves are quantized at the most fundamental level, then the universe operates more like a vast computational process than the mechanical system that classical physics describes. Physical laws become algorithms operating on discrete data, and the evolution of the cosmos becomes a cosmic calculation unfolding step by step according to quantum mechanical rules written at the Planck scale. This computational view of reality suggests that consciousness may play a more fundamental role in the universe than previously imagined. The patterns of information processing that give rise to awareness and understanding may reflect deep principles that operate throughout the cosmos, from the quantum information processing that occurs at the Planck scale to the complex neural networks that enable human thought. The emergence of consciousness from quantum processes may represent not an unlikely accident, but a natural consequence of the information theoretic principles that govern reality at its deepest levels. The mystery of the Planck length also illuminates the remarkable interconnectedness that characterizes the universe across all scales. The same quantum fluctuations that occurred at the Planck scale in the universe's first moments somehow contained the seeds for galaxies, stars, planets, and ultimately the complex chemistry that enabled the emergence of life and consciousness. The boundary that separates the known from the unknowable at the smallest scales connects directly to the larger scale structures and processes that shape the cosmic environment within which awareness could eventually emerge. As we contemplate these profound mysteries, we find ourselves participants in one of the most extraordinary developments in the history of the cosmos, the emergence of conscious beings capable of discovering and appreciating the mathematical elegance that governs reality at its most fundamental levels. The fact that the universe has evolved observers capable of contemplating the Planck length represents a cosmic achievement of potentially immense significance, the development of the cosmos's capacity to understand itself through the medium of conscious minds. The endless pursuit of understanding that the Planck length represents embodies one of the most distinctively human responses to the mystery of existence. Rather than being content with practical knowledge that serves immediate needs, human consciousness is driven by a deeper impulse to comprehend the ultimate nature of reality, to discover the principles that govern existence at its most fundamental levels, and to find meaning and beauty in the mathematical structures that underlie all natural phenomena. In the quiet contemplation of the Planck length, we touch something profound about the relationship between consciousness and cosmos, between the patterns of thought that arise in aware beings and the deep mathematical harmonies that organize the structure of space-time itself. This connection suggests that awareness is not separate from the physical universe, but emerges from it as one of its most remarkable expressions, a cosmic development that transforms matter into mind and enables the universe to contemplate its own deepest mysteries. The journey into the realm of the Planck length leaves us with a transformed perspective on our place in the cosmic order, filled with wonder at the extraordinary nature of existence and humility before the profound mysteries that remain to be explored by future generations of conscious beings drawn to the eternal quest for understanding.